All right, good evening and welcome to tonight's Red Barn event. Thank you all for coming. My name is Dee and I am the Youth Programs Coordinator here at Wenatchee River Institute. We are a nonprofit with the mission to connect people, communities, and the natural world. With me tonight is Jeremy, our main tech person, kind of like the wizard behind all the tech you see over there, and Tucker, one of our community members, educators. They are helping to make it possible for folks to interact with our event at home and record it for later watching or for our YouTube channel. And you may have bought a beverage or buying a beverage from our wonderful volunteer and board member, Paul, over there. Wenatchee River Institute works toward our mission through our youth and community education programs. Our youth programs deliver hands-on curricula up and down the Wenatchee Valley and along the Columbia with our Traveling Naturalist program. About 4 hours ago, you may have not recognized this room because we finished a fall camp. So that's one of the things that we do. And afterwards, we'll transform it back to a fall camp, which will be day 2 tomorrow. Our community programs reach people through our many Red Barn events like this one, our seasonal walks, which one is happening tomorrow at 9 a.m., workshops in the community gardens. Another aspect of WRI is our effort to connect Indigenous peoples to their ancestral lands here. I would like to take time for our land acknowledgements. This land acknowledgement was created alongside the Shimpish-Squashu people. We are spreading the message they wish to be spread to the public. The land Wenatchee River Institute sits on is the ancestral homelands of the Shimpish-Squashu, Pasquosa, or Wenatchee people. The Shimpish-Squashu, meaning people in between, had villages positioned along the Wenatchee River and surrounding areas. Their ancestral homeland extends from the Cascade Ridge throughout what is now known as the Wenatchee and Okanagan Valleys. The culture and economy of the Shimpish-Squashu people centers on taking care of the land. They fish, hunt, gather roots and berries, basket-making materials, and medicines. The Shimpish-Squashu are named within the Yakima Treaty of 1855. Language to establish the Wenatchee Reservation was never followed through, even with the needed surveying completed. Many Shimpish-Squashu now live on the Colville Reservation, 150 miles northeast of Leavenworth. They were forced off their land here, and the U.S. government moved them to this reservation. The Shimpish-Squashu people are still alive today. They continue to practice their culture, harvest their traditional foods and medicines, and hold their ceremonies passed down from their ancestors. Most people won't see or notice them, but they continue to be on the land they are connected to. Their traditional language is Inhamchin, an interior Salish dialect, and we would like to welcome you all by saying hello in their language. Tilhusht. Tilhusht. We offer this land acknowledgement as the first step to amplifying Indigenous voices and recognizing the harm done to them as a people. We stand as an ally to recognize their connection to the land and their rights to practice their culture on these sacred lands. We encourage all to learn about the Indigenous peoples of the place you now call home. The Wenatchee River Institute is committed to sharing this land acknowledgement and following up with other actions to educate and be respectful. I would also like to take time to thank our sponsors, which allow this to happen. So I'm going to read off, which you'll see all of them up here as well. But we'd like to thank the City of Leavenworth, Icicle Brewing, Rhine House, South, North Central Washington Audubon Society, Munchen House, Mitchell Reed and Schmitten Insurance, Oberdal Inn, Chocolat, Tierra Learning Center, Gustav's, Sleeping Lady, Barron House, Cove Resort and Fish Lake, Rimmer and Rotor, Riverfront Rock Gym. It is because of our sponsors and donors that we can reach so many people in the Wenatchee Valley in such diverse ways. As mentioned earlier, this presentation is being streamed over Zoom for viewing at home. During the presentation, please hold all your questions until the end so those audience members at home can hear them. And now to introduce our speaker, who's also one of our board members here. Sarah Doherty is a senior research scientist studying climate at the University of Washington, where she received her PhD in 2001. Her interest in atmospheric science began with a year of work in Antarctica, where she was helping make measurements to better understand the ozone hole. Since getting her PhD, much of her research has involved making measurements of smoke and pollution in different parts of the world, including off the coasts of Africa, China, India, and the Arctic, and understanding how they affect climate. She has also been involved with multiple scientific assessments, including the U.S. National Climate Assessment and 2 international assessments of the state of the ozone layer. In her free time, she likes to spend her time skiing, kayaking, biking, and paragliding, and any chance to enjoy the beautiful area where we live.
And I'm going to talk about climate, which is, maybe not as sunny a topic as some of the other talks you hear here when you get to see color, fall leaves and skiing and all that fun stuff. So I appreciate your coming out. Thank you. And is the sound okay? Okay, good. Yeah, so I want to talk about climate. So I thought I'd start off by just stepping back, which is, we all think of climate as a really complex topic. But really, you can sort of boil it down to some pretty simple concepts. I mean, we're living on this planet that's a ball floating in space. And so the climate of the planet is really about the temperature of the planet. And that's just controlled by how much radiation basically comes into the planet and goes back out of the planet. And by radiation, I mean light. So really, Earth's climate in a nutshell is controlled by really a small handful of things. The amount of sunlight coming in, obviously, how bright is the sun, and how close are we to the sun? So how much energy is coming into the planet? And then the planet's reflectivity, how much of that sunlight gets reflected back to space. And that's, you can see just looking down at the Earth from space, that things like clouds, which are very white, and snow cover, which is very white, will cause a lot of the sun to be reflected back to space. So that has a cooling effect. The darkness of the land or the ocean also matters. So if you have like the dark ocean, the ocean tends to absorb most of the sunlight. So that's quite different from if like you have a desert, which is quite light colored, which reflects a lot of the sunlight. And then there's another factor here that you might not think about, and it's not as obvious from this picture, which is particles in the atmosphere, because they also scatter light back to space, kind of like a thin cloud. So these factors collectively sort of determine how much energy is coming into the planet, how much sun is hitting the planet, and then how much of that sunlight gets to heat up the planet by being retained by the Earth system. And then, of course, the amount of heat being retained is determined by greenhouse gases in the atmosphere. So sunlight hits the Earth, warms up the Earth, and the Earth re-radiates a bunch of that energy back out to space in the form of infrared radiation. And greenhouse gases in the atmosphere absorb and re-emit that infrared radiation back towards Earth and act like a blanket that insulates the planet. And so there's how much sunlight comes in, and then how much of the heat from that sunlight gets to be retained, and that's controlled by greenhouse gases. These are really the factors that determine what the temperature of the planet is going to be. There's a lot of complexity to how they interplay with each other, but that's really fundamentally it. And so I think that we're all familiar with the fact that we've been changing some things about our planet. The big one we hear about is greenhouse gases. And I think we're all aware that by increasing the amount of greenhouse gases in the atmosphere, we're increasing the amount of infrared radiation that is retained by the Earth, and so the temperature goes up. And that's the thing you hear about most when you're talking about climate change and what's driving climate change. But there are other things that we've been doing also that affect climate through changing the planet's reflectivity. When we change land use, take a desert and water it for agriculture, make it darker, that changes the color of the land. And that has a small effect on the amount of sunlight that the planet absorbs. So we're changing the darkness of land through our land use changes. We're changing the amount of particles in the atmosphere. So when we burn things, that produces greenhouse gases, and that's what we're used to hearing about. But it also produces particulate emissions, particulate pollution. And that's also changing the planet's reflectivity. And then less directly, those particles I'll talk about later are changing the properties of clouds and how reflective clouds are. And that's also changing how much sunlight gets reflected back to space. So while what we're used to hearing about is the greenhouse gas changes, there are these other things coming into play, and that's mostly what I'm going to talk about tonight, because they're things that are less familiar to most people, and they are important at this point in time. So particles in the atmosphere, in the science community, we call these aerosols, which is a little confusing to people, but aerosols are just basically particles that are suspended in the air, floating around and scattering light. So that's the term I'll use for most of the talk going forward, is aerosols. So what do aerosols in the atmosphere look like? These are a couple of satellite images that you can see. The image on the left is from India, looking down at India. The wind's blowing from the southwest to the northeast at that time of the year with the monsoon. You can see the Himalayan mountains to the north, some snow on the mountains, and then there's a little low cloud deck at the foot of the mountains, and the wind is blowing the pollution from burning things in India up against the Himalayan mountains and out over Bangladesh and out over the ocean. And you can see that that's causing sunlight to be scattered back to space, that particulate pollution. And that's a man-made cause of increased reflectivity in the atmosphere. Man-made human activities are not the only source of particulate matter in the atmosphere. Wind on the ocean produces sea salt and suspends the sea salt in the atmosphere. And then a big source of particles in the atmosphere is deserts, end up with dust. So that's the picture on the right is the Sahara Desert. You can see on a windy day, you get desert dust is blown up, and where it really has an effect is when it blows out over the ocean. When that blown dust is still over the desert, it's not reflecting a whole lot more sunlight than the desert itself. But when it gets out over the ocean, where you used to have an ocean that's absorbing a lot of sunlight, a bunch of that sunlight is now getting reflected back to space by the particles in the atmosphere. And we're actually familiar with this here. We've all experienced this here. This is Washington State, Pacific Northwest. This is a couple weeks ago. Satellite image you can see on a nice clear day. We have clean air, and we have some clouds over Puget Sound, but it's a nice clean day, and sunlight's being reflected back to space by the clouds. It's being absorbed by the darker plants. It's being reflected a bit by the drier parts of the state. This is Washington State again back in August when we had a really bad smoke event over the whole state from the Canadian fires. And so when we're at the ground, what we experience is less sunlight coming in, obviously breathing bad air, but from space, what we've got is a whole lot more sunlight being reflected back to space by that smoke. So you can see how this is a very intense event, but it's definitely having an effect on how much heat our planet is receiving. You can also notice that there's clouds here in the bottom right-hand corner, and they're very white. Whereas the smoke is a little bit more brown, a little more gray-brown, and I'll get back to the importance of that in a minute. So there's all kinds, there's this whole array of sources of particles to the atmosphere. Some of them are natural. I mentioned sea salt, the wind blows, suspends salt in the atmosphere over the oceans. I mentioned desert dust. When we have volcanic eruptions, that also produces a bunch of particles and spews them into the atmosphere, sometimes very high up in the atmosphere, and causes sunlight to be scattered back to space. There's wildfires. We think of pollution, we more typically think of like vehicle exhaust, industrial emissions. Agricultural field burning is actually still important in a lot of the globe and is a big source of particles, aerosols to the atmosphere. And then cooking and heating in small fires in the domestic environment is also still a source of significant pollution in a lot of the world. So you can see there's a lot of different sources. The composition is really different from these different sources, and the color of the particles is really different from these different sources. So I've talked about how these particles scatter, and shown how these particles scatter sunlight back to space and having a cooling effect. But there's sort of a special case where you have particles that are darker and that absorb sunlight. So a really good example of this, a very extreme example of this, is on the left, where you have a really dirty burning diesel engine, and it's producing black smoke. I'm not sure many of us have seen anything quite that bad, but I think we've all been behind diesel engines where you see black smoke come out. And those particles are mostly light absorbing. So any particles that have color, that aren't white, both scatter and absorb sunlight. And when they absorb sunlight, that warms the atmosphere. And both that absorption of sunlight in the atmosphere and the scattering of sunlight back to space removes sunlight from reaching the surface of the Earth. So both of those processes, both the scattering and the absorption, reduce the amount of sunlight reaching the surface of the Earth. But if there's enough sunlight absorbed in the atmosphere, it can heat up the atmosphere enough that the net effect is climate warming. So if you have dark enough particles, basically, you can get a climate warming effect. And the dark particles, anytime you burn anything, all these images you're seeing here, you're producing a bunch of different chemicals, but one of the ones you're producing is black carbon, something we think of as soot. It's the picture on the left that's very black is basically pure black carbon. But all of these sources produce some black carbon as part of what they emit. And this whole concept sort of triggered about 10 years ago. An effort is an international group called the Climate and Clean Air Coalition. They got together and asked the question of, could we remove this source of black particles from the atmosphere as a way of reducing climate warming? And at the same time, improving health effects, because you'd be reducing particulate pollution at the same time. So this has been a really big topic, actually, of conversation among the air quality and climate community, is whether we could reduce the emissions of these black particles in a way that would take a source of climate warming away and reduce air pollution at the same time. And it turns out that the answer to that question is quite complicated. When you burn things, as I mentioned, you produce a whole mix of stuff. I'm going to give two examples here. On the left is, sort of typical emissions you get out of like a forest fire, grassland fires, agricultural burning, sort of when you're burning biological stuff, and a case of burning industrial coal. So when you burn both of those things, you end up producing some amount of black carbon. But you also produce some organic carbon. There's organic components in both of these. You burn them, you end up with some organic carbon. And those particles, instead of being black, are more brown. And when you burn organic stuff like that, you end up with a lot of brown particles. With coal, just a little bit of the brown particles. And then you also produce some sulfate from the sulfur in each of these things. And when you're burning biological stuff, you don't get very many of those. When you're burning coal, you get more of it, especially in places like China, where the coal is really high in sulfur. You can get a lot of sulfate. And so on net, what comes out is this mix of particles that's somewhere sort of in the brown to gray area. So you almost always have this mix of absorption and scattering. And so really the answer to this question about what the net effect is of these particles, if you reduce the emissions from a given source of all the particulate emissions, sometimes you're going to get warming from those particles, and so reducing their emissions would give you a climate cooling. But almost the only case where that's robustly true everywhere is with diesel engines, because they're producing almost all of the black particles and very little else. They're almost completely producing these black particles, black carbon. And then at the other end, you sort of got this case of like burning biological materials where you have a lot of organic carbon. And most those sources, like the woods, the smoke that we see here from forest fires, is almost always climate cooling. The exception is if those brown particles end up blowing over like snowy areas, very white reflective areas. So if you can imagine, like when we have forest fire burning in the boreal forest regions, and that smoke is getting blown into the Arctic. So you've now got brown smoke over a white surface. That's going to produce a climate warming effect. And so you can target some of those sources to try and reduce their emissions and reduce the climate warming from them. And then there's a bunch of stuff in the middle that it really, really depends on the burn conditions, where it's being burned, and all kinds of stuff. So you'd have to be extremely targeted in which sources of particulate pollution you could get rid of and have a climate benefit. There's, of course, great reasons to get rid of the particulate pollution from all of these. But in terms of climate benefit, you'd have to be really targeted about how you do this if you wanted to produce climate cooling out of reducing these emissions. And so the answer to this question, that is Hillary Clinton in the middle, who led this coalition, is really, you're not going to get a big climate effect out of reducing these sources of emissions. So it's sort of a whirlwind tour around one way in which the climate community has been thinking about these particulate emissions and how they've been playing out in terms of policy. And the sort of the conclusion of that is that, in general, aerosols have a cooling effect on climate by making the Earth reflect more sunlight. That's sort of the net effect of aerosols globally. And there's a limited ability to reduce climate warming by reducing emissions from sources of light-absorbing aerosols, because they're usually mixed with highly light-scattering aerosols. So that's all about how those particles in the atmosphere directly interact with sunlight to affect climate. But there's another way that aerosols, particles in the atmosphere, affect climate, and that's how they interact with clouds, through how they interact with clouds. So all cloud droplets in clouds form on particles. It's not just water. You actually have to have a particle there, and the water condenses onto those particles. So if you form a cloud when you have some moisture in the atmosphere cools off, and that water condenses into droplets. So if you have a fairly clean cloud, meaning you don't have many particles, you don't have much particulate pollution or other particles available, that water all condenses onto the small number of particles, and you end up with a smaller number of large droplets, pretty big droplets. But if you add more particles to those clouds through, say, pollution, you end up distributing that water over those particles, and you end up with a large number of small droplets. And that just basically increases the surface area of water in the clouds, which makes basically just a bigger mirror. So that cloud actually becomes more reflective. So a typical cloud change would go from reflecting maybe 50% of sunlight to reflecting like 55% of sunlight with this type of change. So it's a seemingly moderate change in reflectivity, but in some cases it can be quite significant. And we can see this really visually in some cases. So you can see it's the west coast of the United States. It's on I think late spring, and there's a cloud deck off in the Pacific Ocean. And you can see what look like contrails, those streaks, but they're not contrails. This cloud deck is about 3,000 feet off the surface. It's a pretty low cloud deck. And those streaks are what we call ship tracks. So this is from cargo ships transiting on the ocean. And the fuel that they're burning produces a lot of sulfur. And those sulfur particles mix into the clouds and have this effect that I just described of increasing the number of droplets in clouds and make them brighter, in this case, quite dramatically brighter. And you can see this with some regularity, these ship tracks, and they happen in different parts of the ocean. So that's a really visual manifestation of how human activities are changing cloud reflectivity that really stands out because it happens in these streaks. But this is happening more broadly over the globe, where we have, like off the coast of China, where there's just a huge plume of particulate pollution, or off the northeast United States, big plume of sort of spread out pollution. When that mixes into clouds, it changes the reflectivity of the clouds in a way that you wouldn't notice visually in a satellite image, but is increasing the cloud reflectivity in a substantial way. So I described this process. It turns out this is all a little bit more complex than what I described. If you add particles to clouds, they become more reflective by increasing the number of droplets in the clouds. But a big area of study is actually the complete set of ways that particles being added to clouds ends up affecting the clouds. When you take a cloud and have it have smaller droplets in it, there's a bunch of ways the cloud can respond to having smaller droplets. As you can imagine, if you have smaller droplets in the cloud, it's less likely to rain. So if it's less likely to rain, the cloud holds onto more water, so it becomes optically thicker, meaning more reflective, and it might last longer. So that can add to that initial increase in reflectivity from having smaller droplets. But you can also imagine that if you have smaller droplets, that they'll evaporate more easily. And if they evaporate more easily, you actually lose water in the cloud, so it becomes less reflective. So those two are sort of fighting against each other, and how they balance out ends up depending completely on the atmospheric conditions, so what the meteorology is and how much humidity is in the air and all kinds of other complex things. So there's a bunch of work going on trying to study all these responses of the clouds to having more particles and more droplets in them. So there's a fair amount of uncertainty in this effect on climate. But that's the basics of it. So I've described to you how particles scattering and absorbing sunlight affect climate, how particles affecting clouds affects climate. And so how does it all play out in the climate system? So this is a very complex looking graph, and I'm going to walk you through it in pieces to sort of take it apart. So what this graph is showing is the magnitude and direction of the drivers of climate change, of temperature change, global temperature change, since the pre-industrial period, since the year 1750. And so the bars to the right are showing drivers that produce a warming influence, the red bars. and the drivers to the left produce a cooling influence. And you can see, so I'm going to pick this apart a little bit. So there's a whole section at the top here that's about the drivers that have been from human activities. And then there's a section about natural changes, so changes in solar input from solar cycle changes, volcanic inputs that have affected climate. Both of those things do affect climate, but you can see that over the industrial period, those influences have been really, really small. Those bars are almost invisible. And then at the bottom is showing the total change in temperature from all of these influences on climate since the pre-industrial period. So let's just focus on the larger bars here. Let's get rid of the natural influences, and then there's some human influences in the middle that are just smaller factors that I mentioned, but I'm going to let go for right now to try and simplify this. So the big drivers currently are greenhouse gases, which we're familiar with. The top bar is CO2. It's the biggest greenhouse gas that's driving climate warming. And then there's some other greenhouse gases, methane, N2O, and halogens, which are the things that deplete the ozone layer. Those are also greenhouse gases that are producing a warming effect. Ozone, as in the ozone at ground level from pollution, that also has a warming effect. So all three of those are driving climate warming. And then these effects that I was talking about with aerosols, how we've been changing the concentration of aerosols or particles in the atmosphere over the industrial era, it has produced a net climate effect of cooling. And so the dark part of that bar is that direct scattering of sunlight and absorption of sunlight, which has a net effect of increasing reflection of sunlight back to space. And that has a cooling effect that's moderate, that dark blue section. And then the light blue section, which is bigger, is how particles have been affecting cloud reflectivity. And so you can see, if you look at this carefully, that those effects of aerosols on climate have been offsetting about 1/3 of climate warming from greenhouse gases. So most people aren't aware of that. They think it's all about the greenhouse gases. But if you took away those particles, if we removed all the particulate pollution from the atmosphere, we would immediately have about 30% more warming than we've had so far. So it's a big influence on climate. They're both big influences on climate, but they do have some differences in the way they play out. So when you add these greenhouse gases like carbon dioxide and methane and N2O and ozone to the atmosphere, they have a fairly long lifetime in the atmosphere. CO2 in particular stays in the atmosphere for centuries, decades to centuries. These all have lifetimes of decades to centuries, so they get distributed pretty evenly around the globe, have a fairly even effect around the globe in terms of their concentration. Whereas aerosols don't have a very long lifetime in the atmosphere. Particulate pollution doesn't stay in the atmosphere for very long. And you can see that. I'm going to show you this is not a satellite image. This is a computer model simulation showing the particulate matter in the atmosphere in colors. So it's not the colors they actually are in the atmosphere. It's using sort of a color code to show you what they look like. So you can see the sea salt is getting over the ocean, is getting lifted up by winds and getting swirled around. That's the blue. Desert dust in orange coming off the Sahara and the Middle East and the Tibetan Plateau, a little bit in Australia. It's getting blown around. Those are natural sources. You can see in white industrial and vehicle emissions. In the Midwest and Europe, a lot in China and India, but just generally anywhere there's an urban area or people, you get a fair amount of that. And then these pretty big sources from forest and grass fires, particularly you can see the Amazon, and then in one we don't hear about as much, but Central Africa has a huge amount of agricultural burning. And so you can see smoke coming off there, some Australian fires in Indonesia. But so if you notice, they're really spatially variable. And that's because these particles get lofted in the atmosphere and they get blown on winds, and then they either settle out or they get rained out in rainfall. So they only stay in the atmosphere for sort of 3-4 days, maybe a week, depending on the source. So what that means is if you stop emitting these particulate sources of pollution, they're going to go away very quickly. You stop, if we shut down all industry, that source of particulate pollution to the atmosphere would go away in a week. But the greenhouse gases they emitted would stay for a century or more. So that cooling effect of the aerosols would be removed almost immediately, whereas the warming effect of the greenhouse gases would stay for centuries. And that's an important thing to keep in mind. All right, so I'll end that eye candy. And so I've been talking about all these particles in the atmosphere and how they affect climate, but of course they're a huge source of health impacts. I mean, that's primarily when you think of particulate pollution, you think about it in terms of the health issues, and that is a huge issue. And in the States, in the US and in Europe and many parts of the world, this became pretty acutely recognized, and we've put in place air pollution control regulations to try and address this. So this is, a picture from 1973 in New York City, and then the same location in 2008. And you just don't see days like that really anymore in New York City, except for this summer when they did get smoke from Canada. But this is the Clean Air Act in action. We have really substantially reduced the amount of particulate emissions in the US and in Europe and in some other developed parts of the world. And that has removed a source of human health issues, of environmental issues, and also a source of climate cooling. Now, in much of the world, that's not true. It's really easy living here to forget that air pollution is still a huge issue in most of the world. There's about 2 million people a year die from indoor air pollution. And this is mostly from burning stuff inside for cooking and heating. And most of the people who are dying are women and young children because they're in these enclosed huts cooking by burning dung, coal, and wood, scrap wood, indoors to cook. So this is a really substantial problem. But because of the air quality issues and the health issues with this, much of the world has been reducing particulate pollution in the atmosphere. So this is showing trends in the concentration of aerosols particles in the atmosphere between 1998 and 2012. So fairly recently, substantial reductions. The blue is showing reductions in particulate air pollution. In India and China, up till about 2012, there were pretty strong increases in particulate air pollution. In China, it's actually now starting to, in the last decade, they've started to decrease the amount of particulate pollution in China because of the health impacts and the concerns. So how does this all play out in the climate system over time? So this is showing from 1850 to pretty much present day the time history of the contributions to temperature change in the climate system. So you can see the black dots are the observed temperature change. The gray line is showing the total of all sources of contributions to temperature change. The red line is the greenhouse gases, which sits above the total, mostly because the effect of aerosols has been offsetting a bunch of that warming. And so the effect of aerosols is the cooling. The dark blue line at the very bottom, it almost looks black, has had a cooling influence that's grown over time and is now flattened out and is actually starting to go the other way. That cooling influence of aerosols is starting to actually decline. And as a fraction of the amount of warming from greenhouse gases, it's very significantly declining. So it's offsetting a smaller and smaller fraction of greenhouse gas warming as we go through time. Then there's some other smaller influences that I mentioned, changes in land color, volcanoes, solar input, and ozone pollution has gone up a little bit. But most of this is about the greenhouse gases and aerosols. And while I mentioned that we've already decreased those particulate pollution in Europe and in North America, they're also starting to decrease them in China and India and much of the rest of the world. And the expectation is that in the next couple decades, there will be significant additional declines in particulate pollution because of the health and ecological impacts of that particulate pollution. And because of the turnover in energy sources as we go from coal to solar. Things like that. So we go from burning fossil fuels to using renewables, we're also going to reduce the amount of particulate pollution in the atmosphere. So this removal of air pollution, either through air quality measures or through switching from combustion processes to get rid of CO2, will result in an increase in the rate of warming that is completely dependent on these aerosol effects, not based on what the greenhouse gases do. So where does that leave us? So you probably heard of the Paris Climate Agreement. This is a legally binding international treaty. It was adopted by 196 parties, leaving out only Iran, Libya, and Yemen are the only ones that haven't ratified it yet. In 2015, it went into force in 2016. And the goal is to hold the increase in the global average temperature to well below 2 degrees C, above pre-industrial levels, and to try and pursue efforts to limit temperature increase to 1.5 degrees C, above pre-industrial levels. And so countries have made commitments to emissions reductions moving towards this goal. But right now, the current policies, the current commitments that countries have made, many of which are not being met, I have to say, but the commitments that they've made are projected to result in about 3 degrees C of warming above pre-industrial levels. So we're not doing what we need to do to remain below 2 degrees C, and we're certainly not doing what we need to do to remain below 1.5 degrees C. And the aerosol issue I've just described is only making this worse. So to turn that around, I'm now going to ask the question, could the effects of aerosols on climate be used or leveraged to reduce climate warming in the near term while we get greenhouse gas concentrations down to safer levels? So here's the concept. So if we have a high, like just say a high greenhouse gas emissions trajectory, climate warming going up. Now we put in place aggressive greenhouse gas emission reductions. It will take some time for those to come into play, and will hopefully get us to a point where we are able to stabilize temperatures. But right now we're not doing what we need to do to get there, and we're really looking at pretty impossible to do to remain below 2 degrees or 1.5 degrees C through those efforts alone, unfortunately. And that's pretty broadly agreed now. I don't think the general public understands that. But it is, in the climate sciences community, it's quite broadly acknowledged right now that we really, unless we completely stop emitting greenhouse gases altogether in the next 5 years or so, we are not going to be able to stay below 1.5 to 2 degrees C of warming through greenhouse gas emissions reductions. They are absolutely essential, but if you want to try and meet this goal of staying below 1.5 to 2 degrees C warming, we're not going to be able to do it through greenhouse gas emission reductions only, unfortunately, at this point in time. So then what do we do? So there's this concept of actively removing CO2 from the atmosphere. We are actually pulling CO2 out of the atmosphere industrially, chemically, and sequestering it, either locking it up chemically or putting it into the ground in a place where it's going to be sealed off for a long time. And there are technologies for doing this. This is called carbon dioxide removal, CDR, which involves active CO2 removal. This is a plant that's being built. They have smaller plants, but they're building a bigger one in Iceland. To remove CO2 actively from the atmosphere. Why Iceland? Because they have geothermal energy. So they can do this without producing any CO2 emissions in the process. It's a very energy intensive thing to do, ironically, to pull CO2 out of the atmosphere. So you don't want to do it by burning fossil fuels. You'd want to do it using energy that's not going to be producing more CO2 that you're just going to take out of the atmosphere. So right now they're doing it in Iceland because they have geothermal energy that doesn't produce CO2. So there are technologies that exist for doing this. There's a lot of different people playing with different ways of removing CO2, but it's still very early stages. And the scale of CO2 removal we would need is enormous compared to what we're capable of right now. So just sort of back of the envelope, the current CO2 emissions are just over 37 billion tons per year, and the current active CO2 removal that's going on is about 2 billion tons per year. So it's a small fraction of what we're emitting annually. And what we emit annually, of course, is just accumulating in the atmosphere. Estimates are that to keep warming below 2 degrees C, we need about 1,300 times more CO2 removal in these factories than we currently have. And it's also very expensive, I should say. It's not economically viable at all in terms of the cost of carbon to do that right now. But people are working on trying to make it more economically viable. But you need to scale up very quickly to about 1,300 times more than we can right now. And we'd have to have about twice as much CO2 removed by trees and soils by 2050. And you can imagine how much land that would take and where that would come from. would cover agricultural, you'd be converting agricultural fields, you'd be converting wild forests to forests that are specifically there to sequester CO2. So CO2 removal actively from the atmosphere is something that we need to do probably, but it's not going to solve the problem alone. So this is instigating other conversation, which is the idea of trying to keep warming down through something called solar climate intervention. So what is solar climate intervention? Well, so the concept is, that I mentioned that we're unlikely, we pretty much can't, well, actually, this is well-kept secret is we can't actually, at this point, stay below 1.5 degrees C without substantial carbon dioxide removal, that at a scale that we can't yet do. So that's the dark news for the night. We might be able to stay below 2 degrees C if we do very, very, very aggressive greenhouse gas emissions reductions and carbon dioxide removal. So solar climate interventions. This is the last subject I'll hit on. So solar climate interventions go back to this. The problem we have is greenhouse gases. We absolutely need to solve the problem by reducing greenhouse gases. But a lot of the impacts of climate change are felt or are manifest through the effect of greenhouse gases, which is producing warming in the Earth system. Too much energy retained in the Earth system, too much heating. So with solar climate interventions, the idea is to increase the planet's reflectivity and to sort of take an emergency medicine approach where you're not fixing the disease, but you're treating the symptoms while you're trying to cure the disease, giving yourself time to cure the disease, basically. So the idea is to increase sunlight reflection intentionally as a way of cooling climate to prevent the worst effects of climate change. This absolutely has to be done in parallel with greenhouse gas emissions because it's not a cure or a solution to global warming, and it probably needs to be in conjunction with active carbon dioxide removal. So the approaches that people are talking about for this that would increase, most of them are about increasing sunlight reflection. People have talked about putting basically mirrors in space where you could select the amount of sunlight you're reflecting and where. It would be very expensive to do that. The technology doesn't really exist, so that's not really considered just from the standpoint of the time frame in which we'd need to do it and what it would cost, very viable. The leading method that people are thinking of is leveraging this effect of particles scattering sunlight. You would put those high up in the atmosphere and into a layer of the atmosphere called the stratosphere. It's basically the next layer up in the atmosphere above, basically where weather occurs. You'd put the particles up there and they would scatter sunlight back to space, increase sunlight reflection in cool climate. It's called stratospheric aerosol injection. The second most sort of leading way of increasing sunlight reflection would be through increasing cloud reflectivity through this particulate effect on clouds. So I'm going to talk about those two. So the first one, stratospheric aerosol injection, basically comes from observing this happening in the climate system. When volcanoes erupt, they eject a large amount of mass into the atmosphere. If they're very powerful eruptions, they push a bunch of material into the upper part of the atmosphere and add sulfate particles to the stratosphere. And we saw this in 1991 when Mount Pinatubo erupted. So this is a picture of basically the edge of the atmosphere from the side of the Earth. And you can see it's fairly like blue skies. You can see clouds topping out, and that's like the edge of our atmosphere there. So this is before Pinatubo erupted. And then after the eruption, there was a layer of aerosols at the very high edge of the atmosphere that was scattering sunlight back to space. And this had an effect of cooling the planet by about 0.5 degree C for a few years because of that increased reflection of sunlight from particles in the stratosphere. So this has really triggered the idea of possibly doing this intentionally by taking aircraft and adding these particles to the stratosphere intentionally to cool climate. The difference in the temperature pattern that you end up with and the overall global temperature difference between a world with greenhouse gases and a world with greenhouse gases plus these particles added to the stratosphere. So it doesn't play out evenly over the whole globe. You do end up with some temperature variations. You're going to have some people that benefit more than others. But the globe on the right looks a bit better to me than the globe on the left. There are complexities we need to understand about this and how it would play out, but this is the basic concept. So the other approach is marine cloud brightening. And again, the idea is that you would leverage this effect of particles being added to clouds, making them brighter. I've mentioned this is something that we're already doing unintentionally. But in this case, it would be a targeted application of particles to clouds using sea salt instead of pollution. You'd be specifically targeting low marine clouds. So you'd be doing this in the ocean regions because that's where the clouds are most amenable to brightening with the addition of particles for reasons I won't go into unless someone wants to know afterward. Sea salt's also nice because it's available in the environment where these clouds are amenable to brightening. There's a whole ocean of salt. It's already present in the atmosphere. There's already a lot of sea salt present in the atmosphere and the ocean environment. It's chemically benign and it's readily available. And so there's sort of a cartoon conceptual. This ship does not exist. This is somebody's concept of how this might look. And the idea for this actually came from this seeing ship tracks. People saw this in satellite images many years ago, actually, decades ago, saw this and thought, hey, if we don't get the CO2 problem under control, maybe this would be a way of like reducing climate warming is to do this intentionally, but with sea salt particles instead of with pollution particles. And you would specifically want to do this in a type of cloud called stratocumulus that is over the ocean. And the main target regions would be these sort of 3 orange boxes. This map shows the fraction of this type of clouds over the globe, and you can see there's sort of 3 big hot spots off the west coast of the continents. And so you'd only be increasing the brightness of clouds, the Earth's reflectivity in those 3 locations. But because the atmosphere and the ocean are very efficient at transporting heat, even though you'd only do it in those 3 locations, you could produce global cooling. So this is again a model simulation. If you just increase the reflectivity of clouds in those 3 regions, how much cooling you would get mid-century or could get from marine cloud brightening. And again, you can see the cooling isn't even. There's actually a little bit of warming there in the North Pacific. But mostly you get global cooling, and it produces about a 1 degree C cooling you could get out of this in mid-century. So I just wanted you all to be aware that people are talking about these things or thinking about these things. As scientists, we're studying them. We're trying to study how feasible they are, how much cooling you could get out of them, how they would play out in the climate system, how they would affect climate risks. I don't really know people advocating for using them yet. I think we're all hoping. I'm studying this specific problem right now. I think we're all hoping we don't have to use them, but we're wanting to study them because the ideas are out there, and people may. I think it's likely in a number of decades that when we have enough climate warming going on, that people will know these things exist and be likely to say, let's just use them. And so I would rather understand how they would play out in the climate system first and whether or not that's a good idea. So I'll just close with this sort of slightly lighter slide. Thank you. Questions? Sorry, that was a fire hose of climate information.
I see how effective with solar panels. They're all dark, like on desert, which you say would reflect.
Yeah.
Is there a balance there?
Well, I think the energy you would be getting from those, solar panels are absorbing that and producing energy that would otherwise be produced, by fossil fuels. So I think it's a net benefit, and it's a fairly small area. Yeah.
So the tundra reflects, I assume, more sunlight back than the forest just south of it?
Yeah, it's probably not quite as dark. Yeah. I mean, there are other factors going on in terms of their carbon sink capability and all that stuff too. Is
it balanced out, or is the forest there a net benefit?
Well, the forest is, you have to understand the carbon sink aspects of these things too. So there's different capacities for carbon sink to those different biomes. So it's not just about sunlight reflection in that case. And so that goes back to, so when I showed the original, like what controls the planet's climate, sunlight reflection is in there, but so is greenhouse gases. So if you're changing biota in a way that's changing sunlight reflection, but also changing greenhouse gases by absorbing them or emitting them, which could be the case with like permafrost thawing, then you need to account for that as well. Yeah. It's a fairly complex system.
Are you in conferences with people working on carbon sequestration? Is that part of your
I'm
role or
I'm not really. I mean, it's mostly technology people that are working on that, not climate people, because I mean, the good thing about the carbon dioxide removal is that it's treating the problem. I mean, it's removing the source of the problem. So I hope that those technologies can become more affordable and less energy intensive, and are really able to be used to address the problem. There are people who are arguing that they don't like the idea of the whole carbon dioxide removal concept because it may give us permission to continue to emit greenhouse gases because we can just suck them out. But I don't see that playing out yet, really. And I think if it was 30 years ago and we still had a chance to reduce our emissions in a way that would allow us to avoid dangerous levels of climate disruption, that would be a more valid argument. But at this point in the game, like I said, we cannot stay below 1.5 degrees C of warming, which is a pretty substantial threshold for where you get major climate disruption. We can't accomplish that without significant amounts of carbon dioxide removal. So it's a bit of a, do you want to be a realist or an ideologue kind of argument at
it's
this
kind
point.
of a problem that people 50 years from now could continue to work on if we can figure out carbon sequestration.
Yeah. I mean, really, I think we need to be doing all of these things in parallel. We absolutely have to be reducing emissions. There's no, we're gonna have a hard enough time pulling out, even with significant emissions reductions, we're gonna have a hard time pulling enough carbon out to keep us in a safe zone. So it's not a free pass to just go on that high emissions trajectory. Yeah.
I had a question from online. Kelsey said, "Thank you for this great talk. What do you suggest is the most important thing individuals can do to help fight climate change?"
Yeah. There's so many things you could say there. Voting is really important. I think, we have to, this is a problem that individuals can do, we all can do things individually, but we really do need government level action here, and that means voting. There's a lot of things you can find actually online that are really useful in terms of individual actions. I mean, what you eat matters. There's a huge amount of greenhouse gas emissions from producing meat, beef in particular. Obviously, switching to electric vehicles, reduce, reuse, recycle. I mean, reducing consumption. Air travel is somewhat important, although not as important as most people think it is. Yeah.
It's kind of a lofty question, but the idea of renewables and like the amount of mining that might go into that kind of stuff, and how that then could take like a green dark space and turn it into an open ground space that can no longer sequester carbon, and the amount of work that's going to go into these like mechanical carbon sequestration mechanisms and like human altered climate. What's like your opinion on basically the entire aspect of electricity as a thing, and how we can actually use electricity in a way that's actually like not just human centric? Is that possible, do you think?
That's an enormous question. beyond my expertise, I would say. We need way more efficiency built into things. We need to not be consuming like there's endless amount of stuff to consume to just get energy consumption down. There are absolutely assessments that need to be made about what the environmental damage is with mining for a lot of the things that need to go into renewables. But I will say that, and I would say that's a similar argument to nuclear, which of course has issues with nuclear waste. But with global climate change, you're talking about the whole planet and something that's not easily reversible. So I think you also need to take that into account. I mean, if we're going to have this many people on the planet and we're going to consume things and want to travel and go places, we're going to need to be producing energy somehow. So you're going to have to trade off those things. So unless we all become hermits in the woods, we are going to have to get our energy from somewhere. And yeah, you need to figure out how to do that in the least damaging way. But I think this time scale and the physical scale over which climate change plays out and how long we're stuck with it once those greenhouse gases are in the atmosphere. And that some of the changes we're going to make to climate are irreversible is also something to consider when you're balancing it against, you know, the local damage of mining for, you know, a metal to produce solar panels, for example. Does that make sense? I realize that's not really a great answer, but it's a tough question. It's a very big meta question. Yeah.
Is it true that sea kelp absorbs lots of CO2? And is there much going on with research with ocean and how can we use the ocean to absorb more CO2?
Yeah, there is. There's a lot of work going on. And again, this is outside my area of expertise, but I know that there is a lot of work going on about kelp in particular and using it, you know, much like trees, take up CO2 and sequester it, and having the co-benefits of the ecosystem that kelp provides, often in, you know, putting it back in areas that have been sort of environmentally decimated in particular. So there's a lot of potential co-benefits there, and it can be a food source. So there's, yeah, so kelp is actually one that a lot of people are looking at, but there are others as well. And land-based sequestration. There's you know, I hit on this industrial removal of carbon dioxide, but there are also people really looking into things like how you can change agricultural practices in a way that are environmentally better and also lock carbon into the soil in a way that keeps it there. And the way you use fertilizers and things like that. So there's a lot of small things, and no one of those alone. You'll often hear people saying, well, that's, you know, a small fraction of, that's going to produce this tiny drop in the bucket, but if you put a whole bunch of them together, it really could have effects. And I think that kelp is, you know, is one of them where there's just a lot of potential if it's done right. It's sort of like a lot of net pluses there, and it would act as a carbon sink. So, you know, you can do some tree planting, some kelp stuff, some soil stuff. It's not going to solve the whole problem, but it's going to move in the right direction.
Is it true that kelp absorbs more CO2 than plants and trees?
I don't know that I can answer that question. I mean, I do know it's very efficient because they are looking at using it, but I don't know per, like, is that per tree, per kelp, or is it per pound of tree and pound of kelp? And yeah, so I'm not sure how to answer that. Yeah.
Locally, I feel like there's a lot of controversy about like wood burning, heat versus electric, all these different things.
Yeah.
You mentioned like aerosols and how forest fire can actually like lead to rain or can lead to, you know, like blockage of heat.
Yeah.
What's your opinion on like how locally, how it might factor into like our forest management or like how we heat our homes?
Yeah. I mean, I think the biggest thing locally is, you know, particularly in the valley here, is it tends to be inverted in the winter when people are burning, so that the health impact is probably the biggest thing.
The smoke.
The smoke from people burning. You know, when people are burning leaves and grass and brush in the valley in the fall. It's probably not at a scale that's going to have a substantial climate effect, but it's just the, you know, it's another drop in the bucket. But the bigger influence is probably on health issues in the valley, just because it tends to be quite inverted.
Yeah.
And that stuff gets trapped in the winter in the valley. Yeah.
I know it's complicated, but if as a whole aerosols in the atmosphere have a cooling effect, are forest fires actually helping?
Yeah, I mean, so this is like one of the reasons I think that people don't talk about this aerosol effect very much, is because, like, hey, pollution helps climate, right? So you don't want to demotivate people from cleaning up air pollution. But yeah, this is the sort of the Faust, what is it, a colleague of mine, Jim Hansen, calls it the Faustian bargain. You know, we're cleaning up air pollution, which is a really good thing. You know, for lots of reasons, but we are unmasking a bunch of warming by doing that, and that unmasking happens really quickly.
It's really interesting.
Yeah.
To your other point of like the long tail of greenhouse gases, you could take out the cooling effect, but then the heating effect's going to stay for a long time.
That's right. That's right. Yeah. So if we stopped, like if all human activity stopped tomorrow, what you would initially see is a significant, after about a week, you'd see a significant bump in warming in the climate. And then a slower tail off and stabilization over a longer time period, because you'd initially mostly lose the particles. Your greenhouse gases would stay high, but the particulate pollution would all be gone in a week. So you'd unmask all that warming, and then, now of course we're not going to stop all human activity overnight, but yeah, you'd see an initial significant warming, and then things would stabilize out.
Did you actually see that with COVID, when, you know, factories were shut down?
Yeah.
And people weren't driving? And
That's a really good question. It varied regionally. There were everybody expected that to be the case. There's a little bit of difficulty because there's a lot of variability in particular clouds, so sort of picking the signal out of that one, window where things really, really slow down. But it also turned out there was, like, people were at home, or so they were keeping their heat on all day, so some of the energy production was up, so there were some sources of particulate pollution that actually increased. But there were regions where they did see a notable effect on a notable decrease, a significant decrease in the amount of particulate pollution. A more striking recent case that's actually caused a lot of conversation about the role of particles in climate is in January 2020. There was a new regulation that went into effect for ships. So, if you think about in Seattle, right, we've got Harbor Island and the ships all come in there. And the ships typically, because they spend most of their time in the ocean, get the dirtiest fuel. So they get really crappy fuel. So they produce a lot of particulate emissions, which is why you see those ship tracks. But when they're in port, they're producing all those particulate emissions, and we're causing huge air pollution problems in port cities. So there were stages of rules put into place about trying to decrease that, but there was a big one that went into play January 2020, where they had to reduce the sulfur, which is the source of most of the particles, by 80% in their fuel. And we expected we would see a change in the amount of ship tracks. Clouds vary a lot, so we thought it would take a while to actually pull that signal out, that we'd actually be able to notice a difference. And in 2 years, it was huge signal that you could see the significant decrease in the amount of those ship tracks, and change in the amount of sunlight reflection from those ship tracks. And so that's been a source of a bunch of recent studies. So that's actually in some ways been more striking than the COVID thing. Maybe because they're easier to pick out because they're these kind of linear features. But it's triggered a lot of discussion about just the role in general of particulate pollution affecting clouds and climate. Yeah.
I think for a short time after 9/11, too, there was
So 9/11, yeah.
no airplanes flying.
Yeah, that was an interesting one too. So there's, this is another topic, but okay, so I pointed out how clouds reflect sunlight back to space in cool climate, right? So you have more cloud cover, you have more climate cooling. The one exception to that is cirrus clouds, high altitude clouds. So when you see contrails, those are basically cirrus clouds. They're very high altitude, very thin ice clouds. So if you think about looking down at the Earth from above, they aren't scattering, they're scattering sunlight back to space, but not a ton, not like these lower clouds that are really thick and really white. But because they're really high, when you're looking down from space, they're really high, they're really cold. And so the infrared radiation that's getting to escape from space from the tops of those clouds is not very much. Their biggest effect is that those cirrus clouds actually help retain infrared radiation. So cirrus clouds, those high, thin clouds, are the only type of clouds that actually warm climate. So contrails and cirrus that get produced by contrails have a warming effect on climate. And it's actually, we estimate that warming effect from contrails from aircraft is about comparable to the warming effect from the CO2 emissions of the aircraft. It's that big. But yeah, after 9/11, there was all these people everybody scrambled to do studies of the change in contrails and cirrus in the atmosphere from the aircraft not being up there. It was a really cool experiment to get to do. Yeah.
Sarah, can you talk just a little bit about what the vision of the model of all of these salt spewing ships? Would they follow the cloud bank around, or would they just hang out in one spot because the clouds are always there?
They probably, so those regions that have the clouds that are really amenable to brightening and that there are almost always clouds there, the airflow has a really strong prevailing wind direction, and you would probably sit in one spot underneath and have a bunch of small ships underneath, monitoring the atmospheric conditions to make sure the conditions are right for brightening clouds. They'd spray salt particles, and then those clouds would get blown downwind and stay brighter for 2 or 3 days. And so we're trying to, how the clouds respond would evolve over a few days. So that's one thing that's being studied, is how it would affect the clouds over several days before the particles are lost out of the clouds. And actually those clouds get blown. They start off as in those regions and they get blown out, like the ones off the west coast of North America end up getting blown out towards Hawaii, where the clouds break up and they become little puffy cumulus clouds. And yeah. So you'd probably spray in the one region and it would affect everything downstream for a ways.
Are there field tests? Are we at that stage? No.
No, there aren't yet. So it's all this, the research so far has been in models. There were plans for and hopes to do very small scale studies where you're mostly, that graphic I showed of like the different ways clouds can respond. You'd want to go, what we'd like to do is be able to spray sea salt into clouds in a very small area and just see if we have a good understanding of all those cloud responses, is what we think is going to happen, actually what happens. Not studies where you would actually like change the reflectivity of clouds over a large region and see how climate responds. That would actually be doing climate.
Like a lab study, or it's out in the ocean?
No, out in the real atmosphere, because a lot of the things that are responsible for how clouds respond just happen on scales you could never cover in the lab. Yeah. So I think those are important for making sure that our understanding and our models are correct.
How far to that? How far away are we?
Not sure, because it's a controversial topic, this idea of intentionally trying to cool climate. So there's a lot of discussion in evolution thinking about the acceptability of doing any outdoor studies that are associated with this science area. So, although I will point out that people are doing very similar things a lot right now with, but for a different reason. You've probably heard of cloud seeding to produce precipitation, right? So people are spraying, instead of sea salt, they're spraying like silver iodide or dry ice or some other larger particles into clouds to try and make them rain, which is the opposite of what you'd want to do with marine cloud brightening. And people are doing that for weather modification. There's actually quite a bit of that happens in the southwest US to try and induce snowfall. There's a lot in the UAE, there's a bunch in China, Israel, there's a bunch of dry countries, like China's trying to deal with the fact that most of the rainfall is in the south and they have drought in the north, so they've got a big cloud seeding program. So people are doing this kind of stuff, it's just for localized precipitation, not in the interest of studying how you'd affect global climate. Yeah.
Following on to the question of what we could do individually, and I loved your comment about vote, because that probably is key thing. How responsive are our elected officials to get a nudge from us as voters towards saying, hey, this is something that needs more research, that we should really be spending more time and energy on?
You mean the idea of this increasing sunlight reflection or climate in general?
Yeah, increasing sunlight reflection.
Well, I think it's people in general aren't aware of it, of these options and possibilities, and it would be useful. I think politicians are nervous about approving doing outdoor studies and doing research in this area because they think the public's not going to be okay with it. So hearing from the public that, we think we do have a real climate problem and it would be worth at least understanding if these things would be an option and how they play out in the climate system would certainly be useful. Yeah.
If you weren't held back by any kind of regulation, what would you want to do? Like study next or implement?
Yeah, I showed that bar graph of how humans are changing climate, and I pointed out that the particles are offsetting, the particle effects on clouds in particular are offsetting a significant amount of climate warming right now from greenhouse gases. But what I didn't point out is that there's a huge uncertainty in that. So a lot of my career has been trying to reduce that uncertainty, and colleagues that I work with, we've been trying to understand better how particulate pollution is already affecting clouds. And the difficulty is, so in the introduction it was mentioned that I've gone with NASA, NOAA, NSF, and gone in aircraft and flown with like aircraft that are full of instruments to make measurements and flown off the coasts of Asia and India and Africa, studying particulate pollution in the atmosphere, clouds in the atmosphere, and trying to figure out how those particles are affecting those clouds. And the problem is that, which is going to help reduce those uncertainty bars. The problem is that we are having a hard time, we always have a hard time pulling apart how it is the particles are affecting the clouds versus how other influences are affecting the clouds. So I would really like, even if this concept of marine cloud brightening for climate intervention didn't exist, I would love to be able to go do a study where we actually are able to control the input of particles to the clouds, to be able to do a controlled study to see how the clouds respond to the addition of particles, so we can understand that better and reduce those uncertainties in how particulate pollution is already affecting climate right now and how much it's offsetting greenhouse gas warming. So that's the leading thing, and this is this question of doing outdoor studies. Because we can use models over and over and over, but until we know they're right, we can't really have any confidence in them.
Online from Kevin said there seems to be more intense regional rain and hailstorms. Is this due to increased particulates in the atmosphere?
It's actually the increase in intensity of precipitation, so both droughts and highly intense precipitation events is something we fully expect with climate warming. So it's probably actually not as much about the particulate pollution as it is about climate warming, where you end up with more extreme precipitation as well as more droughts, which seems contradictory, but but you do end up with more extremes with climate warming. Yeah.
So do you live in Leavenworth?
I do.
Okay, and you just work remotely, or?
I'm working remotely, yes. Mm-hmm. Yeah. Yeah, the team I'm working with is all over the place, so we do most of our stuff online anyway. And we have meetings in person at times, but yeah. Okay. Well, thank you for everybody's attention and patience.
Thanks everybody for coming to our Red Barn event. We hope to see you at the next one. Everybody get home safe.
Okay.